Hello, this is Mr. Hammond-Beyer, and this is Lecture 11, Air Pollution, Climate Change, and Ozone Loss. I'll try and keep it to about 20 minutes, the major, and then break it up into a couple of sub-lectures. The main things on today's agenda are air pollution concepts, and we'll talk about the particulate lab at the end. Okay, so what are the questions? The overview questions are, what layers are found in the atmosphere? What are the major outdoor air pollutants and where do they come from? What are two types of smog? And what is acid deposition? And how can we prevent or control air pollution? Here's a picture of an Asian city that I wouldn't want to be in. Look at how bad the smog is in this particular city. Can you imagine the people living there and what their lungs are like after a few years? Even worse, this is Beijing before the Olympics were there. And if you were an Olympic athlete, there's no way that I would want to run in this. So take a few minutes and look at the YouTube video as this is going down. Closer to home, a more usable bioindicator of how bad the air pollution is lichen. And lichen is a mixture between an algae and a fungi living symbiotically in one unit. And there are different forms or shapes of lichen. There's crustose lichen and foliose and fructose lichen. Depending upon the air quality, different lichen will tolerate more or less air pollution. So what you have is a problem after Chernobyl in Russia, when the nuclear reactor exploded and spewed radioactive material into the atmosphere. Much of the tundra in Russia got contaminated by radioactivity. The lichen absorbed that, and the lichen was then eaten by the reindeer, and they bioaccumulated and became very radioactive, so they had to be put down, and therefore the radioactive waste could then be dealt with. So what you have is an exercise on Blackboard called the Lichen Exercise, and I'll ask you to look at these data and graph the distance from the well as the x-axis, and then three lines with fructose, foliose, and crustose lichen, a line for each one of those. And so here's crustose, kind of flat. You've probably seen it if you look on rocks. It'll be the type of lichen that grows on rocks or sometimes on logs. It's flat. Versus foliose is kind of puffy. It looks like little itty-bitty lettuces growing on a lichen. And fructose is much more like fingers or threads moving throughout, and it grows a little bit more and prolifically, shall we say. Okay, now let's look at the atmosphere for just a second, the layers in the atmosphere. And there are four major layers: the troposphere, the stratosphere, the mesosphere, and the thermosphere. The bottom one we live in is the troposphere. The one above us is the stratosphere, the mesosphere, and then the thermosphere at the top. Thermo meaning hot, but that doesn't make sense in some sense of the word, because as you go up in the summertime, if you go from South Carolina up into the mountains of North Carolina, it's cooler, right? So wouldn't you think that the higher you go, the cooler it would get? Well, there are some abnormalities in here, and let's talk about those. So here is sea level, Mount Everest, about 29,000 feet. If you fly from Atlanta to LA, you will probably cruise at about 30 to 35,000 feet above sea level, so a little bit higher than Mount Everest, but still in the top of the troposphere, not really into the stratosphere. In the stratosphere is the ozone layer. The bottom of the stratosphere, the very top of the troposphere is the ozone layer. Then above that, the mesosphere and the thermosphere. Now let's look at the red line represents the temperature. And so you know, in the troposphere, as you go higher, it gets colder. Go to the top of Mount Everest, it's really, really cold all the time. But then as you enter the stratosphere, the temperature starts to increase. And you are now in the ozone layer. Why would that particularly occur? So it warms up, then you get to the mesosphere, and you get to what's called the stratopause, the top of the stratosphere, the stratopause, and the temperature starts to decrease. But then you get to the thermosphere, and look, the temperature shoots way, way up, all the way up to about 120 or 140 degrees Celsius, which is really, really hot, hotter than it is here on Earth. So why can we be, when you go into space, it's so cold that instantaneous freeze, how can it be hot up here? What factors could allow this to be hot? And why would this layer also heat up? Okay, so we are in the troposphere, the innermost layer, and it is mostly nitrogen, 78% nitrogen, about 21% oxygen, and that leaves less than 1% of carbon dioxide, 0.03%. In most cases, water vapor, other things happen to be up there. The ozone in the stratosphere actually filters out most of the sun's UV radiation. So why does the stratosphere start to heat up? It's because the ozone, O3, is in fact up there absorbing UV radiation, and that's heating up those molecules. They break apart into O2 and absorb that heat. So that's why that particular layer is heating up. But why does the thermosphere heat up at 80 kilometers above the surface? So we just answered why the stratosphere, why it should be the troposphere cools down with increased elevation, and what function does the ozone play and perform? So what really does ozone do, and why is it so important? Well, that O3, and I don't know, it's not going to let me do that. The O3 absorbs that ultraviolet radiation. If it didn't, people like me with not very much pigment in their skin would get skin cancer a lot, because all that UV radiation would hit our skin and mutate our skin cells, and we'd have lots of melanomas. So it's a crucial piece. Now, to go to the first question, the thermosphere actually heats up because it is full of ions. And those ions absorb solar radiation, a number of different types of solar radiation. From that, you get what are called the northern lights. So if you ever are up in Minnesota or Canada and you have a chance to be out on an open area and look up to the north and you see the green and the blue iridescence, that is radiation coming from the sun that is absorbed up in the thermosphere. We can't see it here. It's just easier to see up at the poles. But that is blocking much of that other infrared and beyond ultraviolet radiation. Okay, in the troposphere, what are the major air pollutants? Because there are certainly big problems with air pollution. Carbon oxides, that would be carbon monoxide, carbon dioxide. Nitrogen oxides, let's call them NOx. That would be NO, NO2, NO3. And nitric acid, once you add hydrogen to it. Sulfur dioxide, SO2, and sulfuric acid. Suspended particles, matter, SPMs, we'll just call it particulate matter. Ozone, O3, and volatile organic compounds, VOCs. And certainly radon is also a bit of an issue. Where does this stuff come from? So it begins in factories. There are natural sources. Certainly whenever there's a volcanic eruption, all kinds of SO, X, COX, NOx are all emitted into the atmosphere. But also every time we drive down the road, we are putting these into, by internally combusting. Our gasoline is not pure carbon and hydrogen. There is some sulfur and some nitrogen in there, and those blow up with the oxygen and come out our tailpipe and end up in the clouds in the atmosphere. Factories burning, coal-fired power plants are one of the worst, but other factories also produce lots of other compounds. Those would be the hydrocarbons. They all end up in the atmosphere. So primary pollutants are these initial things that come out of tailpipes and out of volcanoes and out of factories. Once they get into the atmosphere, they don't stay as SO2 or NO2. They mix with hydrogen and water, and form acids, which becomes a real problem. And so these are secondary pollutants. There's nitric acid, sulfuric acid, hydrogen peroxide, SO3 forms into H3SO4, which is sulfuric acid, and there's carbonic acid, which is not on here, but that would be carbon dioxide mixed with, or carbon monoxide mixed with water would make H2CO2. Okay, so our primary pollutants then become secondary pollutants. The problems really happen with the secondary pollutants and when those come down to the out of the atmosphere and onto the ground. Okay, so carbon oxides. Carbon monoxide is highly toxic, and it forms from the incomplete combustion of carbon. It doesn't make it into carbon dioxide. Why is carbon monoxide such a problem? Carbon monoxide outcompetes oxygen for binding sites on your hemoglobin in your red blood cells. So if you have carbon monoxide in the atmosphere and you breathe it in, it beats the oxygen to the spots on your red blood cells, so your blood is now carrying around carbon monoxide rather than oxygen, and you literally suffocate to death. 93% of the carbon dioxide in the troposphere occurs because of the carbon cycle. So decomposition of trees and leaves and plant matter and to a much lesser extent animal matter releases carbon dioxide up into the atmosphere. The 7% that is man-made is what is tipping the balance now towards climate change and global warming. And most of that comes from burning fossil fuels. Interestingly enough, carbon dioxide, because so much of it is part of the carbon cycle, the EPA, when it was formed, did not think it was necessary to make regulations to control carbon dioxide emissions. We now know that was short-sighted. Nitrogen oxides, NOx's, NO nitrogen oxide or NO2 can react with water to form nitric HNO3, which is nitric acid, which is, if you drop pure nitric acid on your skin, it will burn your skin. Very, very strong acid. It's not necessarily that strong in the atmosphere, but we'll see how acidic it is. Nitrate salts, so the NO3 can combine with calcium or magnesium or other things that are in the atmosphere and can become components of acid when acid deposition occurs. The third major one, sulfur dioxide, or SOXs, SO, SO2, SO3, form into sulfuric acid. So about a third of the SO2 in the atmosphere occurs from, if you've ever stepped in a mucky pond and bubbles of gas come up and it smells like rotten eggs, well, that's H2S. But so about a third of the SOS or SO2 is in the atmosphere naturally through the sulfur cycle. All right, 2/3 of it comes from us, especially from coal combustion. Because coal has a lot of sulfur in it, it's important to get that sulfur out of the coal when you burn it, either before you burn it or as it goes up the smokestack. You have to pull that sulfur out somehow. Okay, because sulfuric acid and sulfate salts are really, really crucial to acid precipitation. Okay, the other thing are suspended particulate matters, and we'll do an experiment with suspended particulate matters here in just a few minutes on how this works. And they are divided basically based on the size of the particle. So small particles were called PM10s, particulate matter 10, or less than 10 micrometers in length. Really, really fine particles, PM2.5, are the really dangerous ones. So the small particles can get farther and deeper into your lungs, which can cause more emphysema or lots of other lung diseases. According to the EPA, about 60,000 premature deaths a year in the United States alone are because of suspended particulate matter. All right, to give you some clue of this, all right, so here's a human hair which is about between 50 and 70 micrometers in diameter. All right, so we're talking about PM10, so that's a fifth or a seventh of that size. One of those, all right, is a PM10, And of those 2.5, so PM 2.5, there will be 4 of those in a PM 7 or a PM 10 rather. Fine beach sand, you know, when you go to the beach you have fine sand on you, that's 90 micrometers. So that gives you an idea of what size particle we're talking about. What we will, when we sample in our experiment starting today, yes, we'll find some particulate matter that is hair, and that's fine. We might find some grit, and we might find some PM10. I doubt that you're going to have a microscope or a magnifying glass that gets you to see PM10 or PM2.5. Okay, take a look at these particulate pollution clips. They're actually fairly good. A long-term study from 1974 to 2009 estimated that the U.S. could prevent 34,000 premature deaths a year with a 1 microgram per cubic meter reduction. So in other words, if we took 1 square meter of air and we reduced it by only 1 microgram in that whole box, we could reduce 34,000 deaths a year. Okay? 4 in 10 Americans live in counties that contain unhealthy levels of ozone or particulate pollution. The average U.S. value is about 8.4. The healthiest state, if you want to live where it's really, really healthy, go to North Dakota. They're at about 4.5, at least that was before they started fracking. The least healthy state is California at about 11.9 microns per cubic meter. Okay, and that was from 2015 to 2017. One good thing to come out of the COVID-19 problem is here's a satellite image of the NOx pollution in China before COVID came into effect. When everything was shut down, all the industry was shut down in Wuhan and throughout China and Beijing. Notice the air pollution after that. So we could clean up the environment rather quickly if we made that decision. But economically, it would be rather disastrous. Okay? All right, another major air pollution is ozone, O3. And this is a touchy one because it's a highly reactive gas and it can aggravate respiratory illnesses and heart disease, and it can damage plants and rubber and all kinds of stuff. But it's used, you can buy, my wife's a chiropractor, she just bought an ozone machine because she had new carpet installed in her office. And you know that new carpet has to outgas. Well, because this is so reactive, she put an ozone machine in there to get the ozone to react with the gases that were coming out of the carpet to try and oxidize them and make them so you didn't smell, you know, when you walk into a room with new carpet, it smells really chemically. And yes, it's working very, very quickly in her office, but why is it a problem? If you go into a city that has a high ozone level, well, yes, it can aggravate your lungs and your throat and nose. You smell it and you notice right away that there's ozone there. The worst ozone polluted cities, Los Angeles and Long Beach, Bakersfield, Fresno, Phoenix, Modesto, San Diego, Sacramento, New York, and Las Vegas. Notice 6 of the 10 worst cities in the United States for ozone are in California. Why? There must be a reason. You know, New York is number 9 on this, and New York has much more population than certainly Fresno and Bakersfield combined. So what's happening here? We'll have to get a couple steps farther along for you to understand that. Okay, volatile organic compounds are organic molecules. Here's a crude example of this. Okay, I had beans for dinner last night and I have a little gas. That is a volatile organic compound. It has a definite odor and it will oxidize and it will diffuse, but it is a volatile organic compound. If you smell gasoline, the smell is in fact a volatile organic compound. Some volatile organic compounds your body can handle very easily. Some are very carcinogenic. Benzene is the one that's fairly carcinogenic and very volatile. Okay? Vinyl chloride, another one that's used in carpets, is another VOC. Okay, industrial smog is a big issue. And how does industrial smog form? It's a mixture of sulfur dioxide and suspended particles, VOCs, and suspended particulate matter. The biggest source for smog really comes from burning coal. It's terrible. Okay. South Asia, throughout China, has a real serious problem with smog. And they have this brown cloud that sits over them. And there are a couple of video links on your PowerPoint. Please take a look at those. Okay. Here's the formula for photochemical smog. You need VOCs plus NOx plus heat and sunlight. Those then give you ground level ozone and aldehydes and secondary pollutants, which this mix is basically smog. Okay. In Mexico City, which is a high altitude, low latitude city, by running around a lot of cars, they produce a lot of that NOx. They have lots of ultraviolet radiation. Whenever moisture moves in, they have all of the ingredients for that equation, and they end up with a lot of smog. This same thing is what's happening in LA. Okay, that video is actually a pretty good one. Okay, I'd like to speak briefly about how we can stop or reduce outdoor air pollution. Number one, we all need to be driving electric cars. Number two, we need to get rid of all of our coal-fired power plants. Those two factors alone would cut our particulate and outdoor air pollution by 2/3. Are we ready to make all those sacrifices? Not quite yet. Teslas are still a little bit out of my price range, although I'd love to drive one, but how come there aren't a whole slew of electric cars out there ready for market? Another thing that why California had so many high ozone cities was because of what's called thermal inversions. And what happens is, as you increase in temperature or increase in altitude, the temperature should decrease. Well, every once in a while there's an inversion layer which traps a little bit of warm air right above this cooling air, and that keeps all of this air. Think of it as the hypolimnion on a lake. In the bottom of the lake, there's all that stuff that can't escape because of the thermocline. Where'd I go? Okay, well, that's exactly what we have here. This air cannot escape that's coming out of factories and cars and automobiles, and it gets stuck in here, which then increases the smog because the ultraviolet radiation can get in, and there's still a little bit of moisture here, so you have the parts for that equation, and this becomes a big smog belt. Well, what happens is, in California, is you have sea breezes that bring air in, then you have a descending warm air mass, and you have a thermal inversion because the mountains help hold this air in, and you have basically smog accumulate in a number of coastal cities in California. Or, you notice also when there was Reno, the same thing happens in Reno, only you have mountains on both sides, and the air gets trapped in the same method. Okay? So thermal inversion and smog tend to go hand in hand, especially in metropolitan areas. So this video actually kind of explains that. Okay. The next key concept is acid deposition. And sulfur dioxides and nitrogen oxides and particulates reduce or produce or lead to acid deposition. So this stuff goes up in the air, as we saw before, wind comes up and transforms it. So back in the early 1900s, factories didn't have big smokestacks. And so all the people who lived by the factory got all full of soot and had bad air. So they decided, well, let's put it in a big smokestack and send it up. So it goes higher into the atmosphere, which now it becomes not these people's problem, but it becomes the people's problem who live over here. And that's exactly what's happened in the United States. You can see that here is a forest that's been damaged because miles away there are smokestacks that are putting NOx and SOx out in the atmosphere, becoming acid rain and killing all of these trees. Here is the pH of rain from 2000, and notice the pHs: South Carolina 4.5, Georgia 4.5, 4.7, Maine 4.7, 4.8, 4.3 throughout Pittsburgh and eastern or western Pennsylvania, 4.4 in Ohio, but out west you're up in the 5.5s, 6s, much higher. Now, let's overlay on top of that pH map. The red dots represent coal-fired factories, coal-fired power plants. So what in fact is, which way does the wind blow? Well, the jet stream comes from here and comes across and goes this way. So it dips down in the Midwest and moves off to the East Coast. Here is where the coal is being burned to generate electricity. That NOx and SOx is being shunted up into the atmosphere and shifted. And so where are the pHs really, really bad? Throughout here, 4.4, 4.5, 4.7, still bad down here because we burned a fair amount of boy, this just doesn't want to stay still. 4.8 in Alabama, but 4.7 in South Carolina, because this smoke, you know, we get most of our weather from Atlanta, and notice around Atlanta how many coal-fired factories there were, and that sent it over to us. This becomes a real problem if the bedrock, the geology in the area has no limestone. There's no buffering capacity. So here, if we look in West Virginia, 4.5, 4.5, there are a number of trout streams that where the trout died. Cranberry Brook was one of them, because the acid rain dropped the pH in the river so low that the trout couldn't survive, because there was no limestone in the streams. So what did they do? They brought in big piles of limestone and put them in the stream, which then raised the pH of the stream, and they were able to put the trout back in the stream. But out west, the pH is much better because they don't have as many coal-fired power plants, even though in much of Wyoming, they are in fact mining the coal that we're burning over here. Okay, so SOx at atmospheric levels. Notice the high concentrations of SOx in the atmosphere. There are hot spots here in the eastern United States, in Central Europe, and in China. And global acidic precipitation, 4.1 in the United States, 4.2 in parts of Spain, and very, very strong in 5.8 and 4.1 in parts of the Mideast, and even some problems in parts of Africa. So why is acid rain such a problem? Well, it can cause respiratory disease. It leaches metals out of groundwater and can make it very, very toxic. And it is, in fact, causing things like the Colosseum in Greece to literally dissolve. So some of these landmarks that have been around for 2,000 or 2,500 years are now dissolving because of the pH of the rainwater. And here's where acid deposition is a major problem. Eastern United States, throughout Central Europe, parts of China, central parts of Africa, certainly parts of northern South America. Why is this a problem? This is a problem because, all right, so here comes the emissions of acid rain. What happens over time, the soil becomes acidified. The acids go through the soil and leach out the soil nutrients, number one. Number two, they pull out the metals. So if we had a pile of rocks and we wanted to extract the gold out of it, if we add acid to the rock, it extracts out the gold. Well, on the other hand, if that were lead or aluminum in the soil, that would then be leached out and sent into the groundwater, which would then go to the lake. So now we put lead and aluminum into the groundwater, which then, with the pH problems in the soil, that means the tree can't respond very well, inevitably it dies. Okay. All right, so what's the best way to deal with acid rain or acidic precipitation? Is going to be reduce air pollution. If we can stop the SOx and the NOx from getting in the atmosphere to begin with, we can increase the pH, which means, how do we do that? Reduce coal use. Increase the use of natural gas. We have gone to that more recently. And more importantly, we need much more renewable energy sources. Wind power, solar, every house should have a solar panel on its roof. And we should be using solar panels much, much more. And we need to remove the NOx from motor vehicle exhaust. So we all need to be driving electric. Okay, I will stop this video at this point, and we'll pick up the last bits on next Tuesday.